Alrighty, lads and ladies, welcome back to Calc 2. Today we are continuing our slog through sequences and series. So we're into the good shit now, right? We're here. It is my hope that spending a whole week on section 11.2 was sufficient to get you to a place where you're a little bit comfortable with the notation and the concepts behind what series are. So we're moving on today. We are charging forwards. No more 11.2 stuff. From here on out, series are mostly going to be about convergence. Does the series converge or diverge? Because we won't be able to work directly with them. These series will be a little bit too complicated for us to work directly with. We won't be able to find the sum of the series, usually. I won't be able to tell you what most of these series add up to. And I won't expect you to figure out what most of these series add up to. But I will expect you to apply the appropriate tests and figure out whether the series converges or diverges. There will be some cases where we can say a little bit more, but for the most part, that is our goal from here out, is to just look at a series, figure out what test to run, and I'm going to give you a shitload of tests, and then, based on the results from those tests, tell me whether the series is convergent or converges or is divergent. Series diverges. All right, let me turn on the thingy. We can get doing the stuff. Here we go. This is MAC2312. Section number is 004, which means this is Calc 2. And today is the 18th of October, 2021. Today, we're going to talk about the integral test. Which is section 11.3. So you've heard me say many times that infinite series are a lot like type 1 improper integrals. Today, I'm going to show you exactly how much like type 1 improper integrals they are. So I'll just say, recall, I've made the claim smudge this. I've made the claim that sigma n from 1 to infinity an is a lot like integral 1 to infinity f of x dx. The integral is a sum. Sigma stands for sum. You're going from 1 to infinity here. You're going from 1 to infinity here. The big difference is this is this is a discrete sum. It's chunky. It's just like blocks. This is a continuous sum. It's smooth. It's curvy. Here you're adding up countably many things. That's the way we would say it. This is a countable sum. This is an uncountable sum. But I'd like to show you exactly what I mean. So how do we want to start with a picture? By definition, sigma little n from 1 to infinity of a little n is the limit as capital N goes to infinity. Sigma little n from 1 to capital N of an, and integral 1 to infinity f of x dx is the limit as capital R goes to infinity. Integral 1 to capital R f of x dx, which look quite similar. What's more, if f of n when you plug in n for the variable in the function f, if this is equal to an, then both the sum, or say series, and the integral can be understood as measuring an area. So I'll draw you a picture. Here's the curve y equals f of x. One, two, three, 4, 5, 6, and so on. You know, I know, we all know, that the integral from 1 to infinity is trying to find all of this area, right? All the area under the blue curve to the right of x equals 1. Right, the integral is trying to find this pencil shaded area. And when I say f of n is equal to an, what I mean is that the graph of the function and the graph of the sequence match along the sequence. In other words, the orange here is the graph of the sequence an. So this height right here would be like a1, this would be like a2, a3, a4, a5, a6, and so on. Now watch what I can do. The integral is trying to find the pencil area. The series is trying to find the orange area. And of course, the orange area continues on forever also. All of the pencil shaded area bounded by the blue. That's the integral from 1 to infinity of f of x dx. All of the orange area that's the sum. sigma n from 1 to infinity of an. Would you agree that if the pencil area is finite, then the orange area must also be finite? Now we can pretend this guy isn't here. He really doesn't matter. He's just one term. He's necessarily finite. Every other bit of that orange area fits inside the pencil area. So like, what's the area of this first rectangle here? Well, it's the height, which is a1 times the base, which is 1. So this is a1. The area here is a2. The area here is a3. The area here is a4. And if you add all of those up, that is this thing. On the other hand, the integral measures the area under the curve from 1 to infinity. So that's all the pencil area. So this is exactly how intimately these things are connected. Except for the first rectangle, all the orange area, which is the series, fits inside the pencil area. Which is the integral.
Professor,
Yes.
by finite, do you mean each individual term of the series is finite? Because wouldn't the series itself be infinite since it's n1 to infinity?
Well, so the big question with this series is each term finite? Yeah, each term is definitely finite. That's, each term is a number, and one number is necessarily finite. The question is, what about when you add them all up? All the infinitely many terms here. So these orange rectangles, they keep going forever and ever and ever, just like this pencil area keeps going forever and ever and ever. The big deal is that all of the infinitely many orange rectangles fit inside the infinitely long pencil area. So right, both of these things continue on and on forever. But except for the first rectangle, all the orange area fits inside all the pencil area. Therefore, if the pencil area, again, the integral, is finite, and I mean not just like this part of it, but all of it going all the way out to infinity, then so must be the orange area. This is called the integral test. I'm going to give you the exact details in a minute. There are some hypotheses behind it, and it actually is a little stronger than this. But if you understand this, then you will understand what we're doing here. So forget about that first rectangle. He doesn't matter. He's necessarily finite. He's just one term. What I want to know is all this orange area finite when I add all of it up from 1 to infinity? That's my series, sigma an. I want to know, is that finite? Does that series converge? And the neat observation is that all that orange area fits inside all of the pencil area. So if this is finite, then this must be finite. That's the logic. If the integral converges, then the series must also converge. I'll pause for a second here. Are there any questions about what we're trying to convey with this picture? Do we understand what I mean when I say, when I talk about these two areas? either one of these areas could be infinite, right? Since this pencil area goes off forever and ever and ever, it's possible that that's infinite. The orange area also goes on forever and ever and ever. There's infinitely many rectangles. I just didn't draw them all because my hand would get tired because infinity. So either one of these areas could be finite or could be infinite. And our goal is to figure out whether the orange area is finite. And the trick is going to be that we're good at computing integrals. We did a whole section on computing integrals like this. We're not so good at computing series. These are kind of harder to work with in some ways. So if instead of doing the series, you do the integral, whatever is true about the integral must also be true about the series. Turns out it goes both ways. Not only if this is finite, then this is finite, but the other way is true as well. If this is infinite, then this must also be infinite. So let me give you the theorem. Like I said, it has some extra hypotheses. There are some things which must be true in order for these two things to converge or diverge together. And some of those things can be a bit of a headache, but the big picture thinking here is that the integral and the series are very, very similar. So similar that whatever one does, the other must do as well with respect to convergence. So this theorem is called the integral test. This says, if an is equal to f of n, where f of x is we've got three things that must be true: continuous, positive, and decreasing function, then the series sigma n from wherever, I'll say 1 to infinity, an, converges or diverges together with the integral, type 1 improper integral, integral 1 to infinity f of x dx. And I'm going to put a little note here, little asterisk here, little asterisk here. That little asterisk is just if the series starts at n equals 0 or 1, 0, or anywhere else, let's say, then so would the integral. So if you're trying to use this test for a series that is sigma n from 0 to infinity, you would compare to the integral from 0 to infinity. If you're trying to use this test for a series that starts at n equals 2, like n equals 2 to infinity, then you would compare to the integral from 2 to infinity. The lower bound for each of these should be the same. All right. The bitch of it is, before you can use this theorem, you need to show that the associated function is continuous, positive, and decreasing. So for each of these, you're going to lean on some theorems from Calc 1. Continuous, use theorems from section 2.5. Things like polynomials and rational functions are continuous everywhere in their domain. positivity. This is usually pretty easy. Think about the graph. Or features from pre-calc. Like e to the x is always positive, right? That's something you guys know from pre-calc. Decreasing, a couple ways to show this. The main way we show this by verifying that f primed of x is negative. All right, and one more little comment here. The three conditions for the integral test don't need to be true for all x values or even all x values in the domain of integration. They just need to be true the word mathematicians use here is eventually. And what we mean by that is for all x past some number. So if your function is sometimes positive and sometimes negative for x's that are small, but then eventually for all x's, say greater than 10, your function is positive, that's okay. Or if your function isn't always decreasing, but at some x value, it starts decreasing and it stays decreasing forever after, that's good enough. So these three conditions don't need to be satisfied for every x value. They don't even need to be satisfied for every x value from 1 or wherever to infinity. They just need to be true from somewhere to infinity. That's because the part of the series and the part of the integral that makes it converge or diverge isn't the stuff that happens early on. It's the stuff that happens really far away from 0. It's the tail. The tail is the heavy part. It goes on for infinity. It goes on forever. All right, this is the integral test. Please get it in your notes nice and clear. Don't omit any of this. This is your second convergence test. We have the test for divergence, and now we also have the integral test. Last time, I made the claim that the harmonic series diverges. Let me prove that for you now. So we're going to investigate the series sigma n from 1 to infinity of 1 over n. This passes the test for divergence. The limit of the ANs here is 0. So the test for divergence is inconclusive. Let me just show you that, because this is the first thing that we should do when we're given a series, is run the easy tests first. So quick check, the test for divergence. Remember what this says. It says if the limit as n goes to infinity of the an is not 0, then sigma n from wherever, in this case 1 to infinity an, must diverge. Well, here, the limit as n goes to infinity of the and, notice I'm not saying this is equal to the series because it isn't. It's just a thing that we can compute that helps us learn about the series sometimes. Here, the limit as n goes to infinity of the an's is the limit as n goes to infinity of 1 over n, which is 1 over infinity, which is 0. So what can I conclude?
That it converges.
Careful.
Now that it doesn't diverge.
Yeah, not even that. Not even that. So this says if the limit is not 0, then the series must diverge. If the limit is 0, we don't learn anything. Right? So I could say, if you give me a lighter, I will burn down the school. If you don't give me a lighter, I could still burn down the school. Maybe I got my own, right? This says, if the limit is non-zero, then the series must diverge. Well, okay, the limit is 0. So the series could diverge or converge, either one. We don't learn anything. This is inconclusive. And be careful. There's a reason I ask this question, because it is such a common trap. The limit of the an's being 0 is inconclusive. If this limit came out to anything other than 0, then I could say the series diverges. But if the limit comes out to 0, it could go either way. So instead, I'm going to use the integral test. How do you use the integral test? Well, first, you have to find your associated function. The an here is 1 over n. And that is equal to f of n for f of x equals 1 over x. So this sequence can be thought of as coming from this function just on the natural numbers. So here's the function we're going to work with in our integral test. We have to show that this is continuous, positive, and decreasing, at least eventually. Now, here it's easy. Just look at the damn graph, right? We know what the graph of 1 over x looks like. I sure shit hope we do. I beat up on my pre-calc kids if they don't know this graph. So you guys, Calc 2 students, here's the graph of 1 over x. From the graph, we see that f of x equals 1 over x is continuous, positive, and decreasing for all x greater than 0. Right? I'm just looking over here. Is this curve continuous, positive, and decreasing? Yes, it is. Continuous, it's unbroken, right? The only place where this function is discontinuous is at x equals 0. But I'm not interested in 0. I'm looking from 1 to infinity. Is this function decreasing? Yeah, it's decreasing everywhere, but in particular, from 1 to infinity, it's definitely decreasing, right? Here's 1. So are we continuous, positive, and decreasing? Yes, just look at the graph. It's not always going to be this easy. Sometimes you will have to use that derivative work to show that the function is decreasing. Or sometimes you will have to use theorems from 2.5 to show that your function is continuous. But here we know the graph, life is good. So because that function is continuous, positive, and decreasing, therefore, the series sigma n equals 1 to infinity 1 over n, and the integral integral 1 to infinity 1 over x dx do the same thing. They converge or diverge together. That means if the integral converges, then the series converges. If the integral diverges, then the series diverges. They're not equal to each other. Right? They're not equal to each other. Don't tell me these things are equal to each other. They are not. But they do the same thing with respect to convergence. I could work with the series to show something about the integral, but I'm trying to learn about the series. The problem here is that I don't know what's going on with the series. My goal is to investigate this series. So what we do is we work with the integral to learn something about the series instead. Right? That's why we call it the integral test. Now, integral 1 to infinity 1 over x dx is equal to the limit as r goes to infinity, integral 1 to r 1 over x dx, which is the limit as r goes to infinity, natural log absolute value of x evaluated from 1 to r. Which is limit r to infinity, natural log of r is positive here, it's going to infinity, minus the natural log of 1. 1 is positive, and natural log of 1 happens to be 0. What is this limit? We've used this limit several times here. What does the natural log of r do as r goes to infinity?
It also goes to infinity.
Also goes to infinity. Thus, the integral from 1 to infinity 1 over x dx, is this a convergent integral or a divergent integral?
Divergent.
Very good. So by the integral test, our series S equals sigma n from 1 to infinity 1 over n must also diverge. And pay attention to the language and the notation I'm using here. Again, all throughout chapter 11, the language is at least as important as the calculations. Are there any questions about this use of the integral test?
Can we say that the series is contained within the function?
Not quite, but almost. Yeah. So if you want to look at the actual picture here, it's almost true that the series is contained within there, but there's this first term that's being measured by the series, which isn't being measured by the integral. The integral is measuring just the stuff to the right of 1. The integral is measuring like all of this blue area. So there's a little part of the series that isn't contained within that integral, but this little part of the series is just one number, so it's necessarily finite. So it's true that the rest of the series is contained within that integral. That is true. The exact relationship between the series and the integral is discussed in the textbook. There's two inequalities. Let me show you. All right, I found it. If you're not stressing the details, you're not stressing the details, and that's okay. The important thing is that you know how to use the test. But since you asked, where's the general picture? Here it is, proof of the integral test. So there's kind of two ways to arrange this. There's a way to, if I shift the series to the right, then I can make the series look bigger than the integral. If I shift the series to the left, I can make the series look smaller than the integral, right? A1 would be this height right here that they haven't drawn, and they're just showing from A2 on. So the exact relationship between the series and the integral is described in terms of the partial sums. The partial sum for the series, omitting the first term, is smaller than the integral from 1 to n. And the partial sum of the series omitting the last term is larger than the integral from 1 to n, which means that the partial sum overall has to be smaller than the integral from 1 to infinity plus a1, plus that first term. And the second inequality shows me that the partial sum out to n minus 1 is larger than the integral from 1 to n, which means that you can kind of sandwich the partial sums of the series between two very closely related integrals. But it's not necessarily true that the integral contains the series, although it is very, very close to being true. The big thing is that they differ by a finite amount. All right, so if two things are different from each other by a finite amount, then if one of those things is infinite, the other thing is infinite. And if one of those things is finite, the other thing is finite. Like if you have $1 less than me and I have infinity dollars, you also have infinity dollars. And if I have a finite number of dollars and you have $1 less than me, then you also have a finite number of dollars. Maybe a bad analogy, but I think it works.
Thank you.
Sure, of course. All right. This integral that we used here, this is a special kind of integral. This falls into a family of integrals that we know well. What family of integrals does this fall into? Anybody remember the term? There's a dick joke in here somewhere. I'll find it for you in a minute. Yeah, in the chat it came in as a DM. It's a p integral. This is a p integral with p equal to 1. So what we're about to discover is a relationship between that big family of integrals called p integrals and a big family of series called p series. This is a definition. Series of the form sigma n from 1 to infinity, 1 over n to the p, are called p series. If there's anything else going on in here, like some other stuff upstairs besides 1, or some other stuff downstairs besides n to some power p, then that ruins the p-ness of the p integral, or the p series. What makes this a p series is that it's just sigma 1 over n to the p. This n could start at 2 or 3 or 4, it doesn't matter, but the summand has to just be 1 over n to the p. Yeah. P series converge if p is strictly larger than 1 and diverge if p is less than or equal to 1. Why? Because we can immediately relate them to p integrals using the integral test. Proof. Let S be sigma n from 1 to infinity, 1 over n to the p. and apply the integral test. An in that series is 1 over n to the p is equal to f of n, where f of x is 1 over x to the p. For any positive number p, f of x has a graph which in the first quadrant looks like the 1 over x graph. So f is continuous, positive, and decreasing for all x greater than 0. Thus, the series sigma n from 1 to infinity, 1 over n to the p, will converge or diverge together with the integral from 1 to infinity, 1 over x to the p dx, which is a p integral. I don't even need to do the computation because by a previous theorem, p integrals converge if p is greater than 1 and diverge if p is less than or equal to 1. Thus, the series sigma n from 1 to infinity, 1 over n to the p, converges if it does the same thing as the integral, right? It does the same. Converges if p is bigger than 1 and diverges if p is less than or equal to 1. And that's the proof. So series like this, p series, by the integral test, do the same thing as p integrals. P integrals converge if p is bigger than 1 and diverge if p is less than or equal to 1. Since p series must do the same thing as p integrals, p series must converge if p is bigger than 1 and diverge if p is less than 1 or less than or equal to 1. The parts here that I need you to remember definition and the statement of the theorem. You should also digest the proof, because there will be problems in your homework that ask you, I give you a big family of series and I ask you for what values of p does this family of series converge? Very similar to those problems from section 7.8. Remember the 1 over x times the ln of x to the p integral, where I asked you for what values of p does this integral converge? I can ask you that same problem with the integral swap for a series. And your argument would be very similar to this. What's more important is that these p-series form a basis for comparison. You remember we have a comparison test for type 1 improper integrals. If you're smaller than a convergent integral, you're convergent. If you're larger than a divergent integral, you're divergent. And most of the time when we solve problems with those, the way we solve them is by taking our complicated integral and comparing it to a p integral. Well, we're going to do a lot of that with series in section 11.4, the next section. But before we go there, I want to get you more practice with the integral test. I want to show you how those hypotheses can sometimes be a bit of a headache, but also why they're necessary, because if you don't have those things, then the series and integral may not be connected to one another. Questions on the definition of a p-series or the theorem on p-series? Okay. Let's look at an example or two. Seven looks good. Let's look at number 7. Again, in your mind, kind of the first thing you want to do is run the test for divergence. The ANs here are n over n squared plus 1. Do those go to 0 as n goes to infinity?
It's a determinant.
Right, yeah, if you just plug in infinity, you get an indeterminate form. So let's actually do it. Let's write it out.
But yeah, it does go to 0.
Yes, it does. So the limit as n goes to infinity of the ANs is the limit as n goes to infinity of n over n squared plus 1. This looks like infinity over infinity, which is indeterminate. It's an indeterminate ratio. So we could, if we want to, apply L'Hopital's rule. And we see that this is the same as the limit as n goes to infinity of 1 over 2n, which is 1 over infinity, which is 0. So TFD, test for divergence, is inconclusive. I keep saying this because I really want to drive it home. Please remember that if the ANs go to 0, the test for divergence is inconclusive. We don't learn anything. Does not mean that the series converges. And this shows up as a true-false question every time on exam 2, and I catch like half the class on it every time. So please don't let that happen. The only other tool I have can't factor n squared plus 1, right? So there's no way this could be a telescoping series. The only other tool I have is the integral test. Now, my related function here, an, is n over n squared plus 1, which is equal to f of n for f of x equals x over x squared plus 1. Here, we're going to actually have to do some work to show the continuity, positivity, and decreasing. It's not immediate. Maybe you know what this graph looks like. I know what this graph looks like. Maybe you've seen it, but probably don't remember it, and that's okay. So I'm doing this example to show you how to actually go through those things. Continuous.
What if we apply the integral test without seeing if it is positive, continuous, and decreasing?
Well,
Are
if
we gonna be stuck in a loophole, or is it just gonna give us an answer that it might not be 100% right?
the second one. If that function is not continuous, positive, and decreasing, then it's possible for the integral to converge and the series to diverge. If those three conditions are not met, then the series and integral are not tied together. Right? So I could give you a problem where the corresponding function fails to be continuous, and then you get a divergent integral, but the series converges, so you get the wrong answer. So these three requirements are meaningful. Without them, the two objects, the series and the integral, are not connected. So we need these things to be true in order to say, since the integral converged, the series converged, or since the integral diverged, the series diverged. Without those three things, those two objects are not connected. So f of x is a rational function. Remember, rational functions are ratios of polynomials. These are continuous everywhere aside from when the bottom is 0. Here, the bottom is x squared plus 1, which is never 0, at least not for any real number x's. Therefore, f is continuous on the whole real line, negative infinity to infinity. So not only is this function continuous from 1 to infinity, it's continuous everywhere. Positive. F of x is equal to x over x squared plus 1. The bottom, x squared plus 1, is always positive. You know that x squared is always greater than or equal to 0 because squares are always non-negative. So x squared plus 1 is always greater than or equal to 1. So f of x equal x over x squared plus 1 will be positive. If you have a fraction where the downstairs is always positive, then the whole fraction will be positive if and only if the top is positive. And since the top here is just x, that means if and only if x is greater than 0, i.e. f is positive on the interval 0 to infinity. If the top was x minus 1, then this function would be positive on the interval 1 to infinity. Either one of those would suffice for us, right? We want to see that this function is positive eventually. And what we learn is that it's positive for all x's bigger than 0, which is definitely good enough for us. That is eventually. That's more than we need. Decreasing. This function is not always decreasing. The graph of this function, I'll draw it for you in the air here. The graph of this function looks like this. It goes, right? It's called the witch of Agnasi. It's got this kind of funky little S-curve shape, and it's got horizontal asymptote y equals 0. It approaches from above on the left, or sorry, above on the right and below on the left. We need to, so this is all Calc 1 and pre-calc shit, right? Saying that this function is continuous because it's a rational function, which means it'll be continuous everywhere the bottom isn't 0. The bottom is never 0, so this function is continuous everywhere. That's a pre-calc thing. Positivity, saying this fraction will be positive if and only if the top is positive, because the bottom is always positive. Again, kind of a pre-calc thing. You're solving an inequality here. You're trying to figure out where this function is greater than 0. That's a pre-calc thing. Decreasing, this is going to be a calc thing. F is decreasing if f prime is less than 0. This is a fact from Calc 1. And here, f primed of x is what? Well, we're going to use the quotient rule, everybody's favorite derivative rule. The bottom is x squared plus 1 all squared. Remember what your quotient rule says, low d high minus high d low. So that's the bottom times the derivative of the top, x squared plus 1 times the derivative of x, which is 1, minus the top times the derivative of the bottom. Well, the top is x, and the derivative of the bottom is 2x. So this is x squared plus 1 minus 2x squared, which is 1 minus x squared. All right, x squared minus 2x squared is negative x squared. So this is my derivative. Let me continue this over here. F prime of x is 1 minus x. I'm going to factor the top times 1 plus x. The bottom doesn't factor, over x squared plus 1 all squared. So you guys remember how to do this? You make a number line. Your critical numbers here are positive 1 from this factor, negative 1 from this factor, and you don't get any critical numbers from the bottom. F prime is never undefined. So you make a number line for f primed. You plot the critical numbers on that number line. Here's negative 1, here's positive 1. And that chops your number line up into 3 regions. And then you can either test a point from each region, or you can use factors and multiplicities. You're going to need to test at least one point. If I plug in x equals 0, what is f primed of 0? It's probably easier to see here. F primed of 0 is 1 minus 0 squared over 0 squared plus 1 all squared. That's 1. So my derivative is positive between negative 1 and 1. Over here, if you test x equals 2, f primed of 2 is 1 minus 2 squared is negative 3, divided by 2 squared plus 1 is 5 all squared is 25, which is negative. I don't give a shit what's going on over here. Turns out it's decreasing, but I don't give a shit what's going on to the left of negative 1. I'm only interested in what's going on from 1 to infinity anyway. So f is decreasing from x equals 1 onward, i.e. on the interval 1 to infinity. So is my function decreasing? Not everywhere, but from 1 to infinity it is, which is good enough for us. My series starts at 1, so this would be ideal anyway. Even if this was like from 10 to infinity, that would be okay, because we just need these things to be true eventually. All right. This is where most of the work actually lies in the integral test. The vast majority of these problems, most of the time, is going to go into showing these 3 conditions are met. Are there any questions about how I showed these 3 conditions to be met here? Okay then. So now that these 3 conditions are met, I can say that the integral and the series do the same thing. Thus, sigma n from 1 to infinity n over n squared plus 1, and the integral 1 to infinity x over x squared plus 1 dx must converge or diverge together. I still haven't answered the question, does the sum converge? I've just shown that the series does the same thing as the integral. So now I need to compute this integral, or at least determine whether the integral converges or diverges. Once I know that, I can now, because we've shown these 3 things, say that the series does the same thing. Now, integral 1 to infinity x over x squared plus 1 dx, by definition, is the limit as capital R goes to infinity, integral 1 to capital R x over x squared plus 1 dx. How do you do this integral?
U sub.
U sub, very good. I'm going to use the symbol z. U sub for the bottom, x squared plus 1. dz is then 2x dx. We also need to change our bounds. When x is equal to 1, z is equal to 2, and x is equal to r, z is equal to r squared plus 1. So this becomes lim r to infinity 1/2 from my differential, integral from 2 to r squared plus 1. The x dx gets gobbled up by this differential, and this 2 gives me this 1/2. I'm just left with 1 over z dz. So this is, I'll pop the 1/2 out further, 1/2 lim r to infinity. The antiderivative of 1 over z is the natural log of z. So this will be the natural log of r squared plus 1, eschewing absolute values here because r squared plus 1 is definitely positive, minus the natural log of 2. Okay, this limit is similar to the limit we had to do for the previous problem. As r goes to infinity, what does the natural log of r squared plus 1 do?
It also goes to infinity.
Also goes to infinity, right? If you want, you can write this as the natural log of infinity minus the natural log of 2. Just thinking about one thing at a time sometimes helps. So as r gets bigger and bigger and bigger, r squared plus 1 gets bigger and bigger and bigger. So the r squared plus 1 piece is going to infinity. So I can just write it like this if I want. And then the piece that I require you to remember, right, the thing that sometimes we forget is that the natural log goes to infinity as its inside goes to infinity. So this is infinity minus the natural log of 2. How big is the natural log of 2? Just roughly.
About 1.
Yeah, it's smaller than 1 even. It's like 0.69, because the natural log of e would be 1 and 2 is smaller than e. So this is definitely infinity, right? 1/2 times infinity minus some small number, shit's definitely infinity. In particular, the integral 1 to infinity x over x squared plus 1 dx diverges. So by the integral test, the series S equals sigma n from 1 to infinity n over n squared plus 1 must also diverge. That's the job done. And you see, this is quite a bit of writing. Took about a half page to show that we could use the integral test, to show that this function is continuous, positive, and decreasing. And then it took about another half page to compute the integral and just state the result, that because the integral diverges, the series must also diverge. You cannot skip any of this. It is just a fact that writing out these solutions takes up space, takes up time. Have I shown you this callus? Right? Welcome to the world of mathematics. This is just your life, right? This is your life now. Everything is fine. Be patient. You're going to have to write a lot. That's okay. You want to practice writing this shit. You do not want to be skipping over stuff, because then when it comes time for the test where you have to do these things correctly, I'll be taking points off for everything you skip. Every time you leave off a limit, every time you forget to say that these things converge or diverge together, every time you forget to say by the integral test, points are coming off. Please practice using good logic, right? It's important. Use good notation, good logic, write in full sentences. Do not just go through the homework clicking converge or diverge. You will bomb this test. Frank asks a really good question in chat. What do we do if this function is not continuous, positive, and decreasing? Well, remember, first, the function doesn't always need to be continuous, positive, and decreasing. Like here, my function was increasing from -1 to 1, but decreasing from 1 onward. As long as those conditions are satisfied eventually, you can still use the integral test. But if any one of those conditions is not satisfied from some x onward, then we got to do something else. We can't use the integral test. The integral test does not apply. Another good question in chat, how long should a problem like this take? The first few that you do could take you an hour, could take you an hour each, and that's okay. But after you get comfy with them, I would say 10 minutes-ish. Here I'm writing out every gory detail, right? And I'm restating things over and over again. After you get practice with these, I'd say 10 minutes-ish for a reasonable difficulty problem. Sometimes that integral is very hard. Sometimes that integral is on its own a massive challenge, and that might take longer. So it varies from problem to problem, but I would say around 10 minutes. Let's look at number 14 here. I'm going to copy it down, then we'll switch back to the dot cam. This series has not been given to us in sigma notation. It's 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus 1 over 4 root 4 plus 1 over 5 root 5, and so on. So if I'm going to use any of the tools that we've learned so far, test for divergence, any of this shit, integral test, first thing I need to do is write this in sigma notation. I need to know what the ANs are. So first, observe that S equals 1 plus 1 over 2 root 2 plus 1 over 3 plus 1 over 4 root 4 and so on is equal to 1 over 1 root 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus 1 over 4 root 4 and so on. Right, this guy fits into the pattern that the rest of them fit into. It's just that 1 times the square root of 1 is 1. Now, in general, a times the square root of a is a to the 1 times a to the 1/2, which is a to the 3/2. Here's the algebra rule. All right, something times the square root of itself is that thing to the 1 times that thing to the 1/2. So this is 1 over 1 to the 3/2 plus 1 over 2 to the 3/2 plus 1 over 3 to the 3/2 plus 1 over 4 to the 3/2 and so on. So somebody tell me now, how do I write this series in sigma notation? Fill in the gaps. What are my ANs?
One over n to the 3/2.
Very good. Where does my series start?
At 1.
Very good. What kind of series is this?
Geometric.
Eh,
No?
nah, not geometric. Remember, geometric
P-series.
is like some constant raised to the nth power. I heard a different answer. What was the other answer?
P-series?
Very good. This is 1 over n raised to the p, where p is 3/2. How big is 3/2?
Greater than 1.
Definitely bigger than 1, right? 3 is bigger than 2. The top's bigger than the bottom. So this number is bigger than 1. It's 1.5. But most importantly, it's bigger than 1. Therefore, by our theorem on p-series, this series S must converge. That's pretty dope, right? That happened real fast. All we had to do is recognize that the thing is a p-series. All right. So I think this is enough for today, which is convenient because we're just about running out of time. I want to describe to you a little bit where your strategies should be at this point. If I hand you a series and you have no context, like it's not coming from this section or that section, the first thing you should do is ask, is this series geometric? That's easy, right? Is the series some constant raised to the n, sigma, some constant to the n? If it is geometric, that's great. We know everything about geometric series. You appeal to that theorem. If the series is not geometric, you should ask, might this be a telescoping series? Can I do some partial fractions on the ANs? Does it look like for maybe some other reason there might be a lot of cancellation? We've seen plenty of telescoping series at this point from last week's homework. We know what they look like. If the series is telescoping, you write out the nth partial sum and then clean it up. right? Telescoping series means that that partial series sum will clean up nicely. And then you use the definition of an infinite series, saying that the infinite series is the limit of the partial sums, compute that limit, and write down the result. If the series is neither geometric nor telescoping, then we're on to the test for divergence. And you should look at the ANs and ask, do the ANs go to 0? If that limit is not immediately obvious to you, then you should write it out, like we did on the last two problems before this. We wrote out the test for divergence, we took the limit of the ANs. In both of those cases, the ANs did go to 0, which remember means test for divergence is inconclusive. If the ANs go to 0, we learn jack shit. But if the ANs don't go to 0, then you can say the series diverges and you stop, you're done. If the series is not geometric, not telescoping, and TFD is inconclusive, then you appeal to the integral test, where you must show that the corresponding function is continuous, positive, and decreasing. And then you compute the relevant improper integral. If that improper integral is convergent, the series is convergent. If that improper integral is divergent, then the series is divergent. This is where we are right now. The other thing you should be mindful of, like this last problem shows, check and see if your series is a p-series. I would say this is at the same level of, is my series geometric, or is my series a telescoping series? So I should have said that, I'm sorry. Yeah, check to see if your series is geometric. If it's not, check to see if it's telescoping. If it's not, check to see if it's a p-series. Usually it's pretty easy to spot a p-series. Like this is a p-series, right? It's 1 over n to some power. That power has to be constant. This is a p-series. You have to rewrite it as 1 over n to the 0.99999, but then yeah, that's a p-series. If your series is not geometric, not telescoping, and not a p-series, then you've got the test for divergence and you've got the integral test. And you can work any of these using those. I'm going to give you more homework. The homework that I'm going to publish this week is going to be 11.3 and 11.4. 11.4, kind of tricky. 11.3, not too bad, but you got to remember that pre-calc and calc 1 stuff, because if you don't show your function is positive, continuous, and decreasing, you're boned. Counter examples exist. Number 27, this series, you cannot use the integral test on it, because cosine of pi times n, this blinks back and forth between +1 and -1. The associated function here, cos pi x over square root of x, is not a positive function. The integral that you would get if you just blindly wrote down the integral test for this series, I think is divergent. But this series, and I'll be able to show you when we get to 11.5, this series is a convergent series. Similar issues exist here. This function is not decreasing. The associated function cos squared x over 1 plus x squared is not a decreasing function. It wiggles quite a bit. And in these cases, the integral and the series don't do the same thing. Finally, problems like this are good problems. I'll put 1 or 2 like this in your homework, and you should take them quite seriously. Spend some time really working with these and make sure you understand them. You'll recognize this one as being very similar to the problem from improper integrals. And I'll pick one of the other different ones. This is a fun one, but it's a little gnarly. Probably we'll do something like this. In any case, please sink some time in between now and Wednesday, because on Wednesday, we're going to be talking about something totally new. There's going to be 2 new convergence tests on Wednesday. They're both called comparison tests. One is the direct comparison test. The other one is the limit comparison test. And our kind of basis for comparisons will be geometric series and p-series. So you need to be comfy with this stuff in order to move on. So that is it from me for today, gang. I'm going to go ahead and let you go here. Please, if you're not caught up on the homework, get caught up as soon as you can and begin on the homework for this week. That's it. I'll see you all.
Office hour today?
Yeah,
office
office
hour?
hours 1 to 2. Yep, normal office hours.
Nice.
All right, take care, gang. See you Wednesday.